Hey everybody. So I've got the equation of ellipse graphed in Desmos, and I'm going to change one little thing about it. Let's see what happens. Maybe. There we go. Here it is. All right. So x squared over 25 plus y squared over 9 equals 1. That's the equation of ellipse. We should be very familiar with it. But I'm going to change one thing I said. I'm going to change that plus to a minus. And what does that do to the graph? Changes the entire thing, giving us what we call a hyperbola. All right, so we get this really neat graph when we switch that plus to a minus, which is called a hyperbola. Kind of looks like two parabolas, but they're a little bit different. They're not parabolas. They come in though, they have a curved portion here where they come out and they actually approach two diagonal asymptotes, oblique, diagonal, slant asymptotes, whatever word you want to use to describe those. So let's get to the details. Okay. When we look at a hyperbola, okay, and here we have one that's much wider than the one that I graphed, we have a vertex at there and there, so two vertices. Okay, just like ellipse had two vertices, a hyperbola has two vertices. The covertices are actually not a piece of the graph itself, but are right here and here. And when you graph the vertices and the covertices, it actually ends up making a rectangle here that helps us sketch out the graph, because through the corners of the rectangles, we get our slant asymptotes. Okay? There are two foci. There is a focus on each half. There's a focus here that it wraps around, and a focus here that the hyperbola wraps around as well. Now, the axis connecting the vertices is called the transverse axis. That can be horizontal like it is here, or it can be vertical instead if the hyperbolas will open up and down. We have a conjugate axis going the other way. I won't really use that term. So what does the equation look like? Well, the equation looks like x squared over a squared minus y squared over b squared equals 1. Okay, that's the graph of this. And when that's the case, our vertices are at a comma 0 and negative a comma 0, just like in an ellipse. The covertices, just like an ellipse, are at 0b, 0, negative b. The focus is at c0 and negative c0, just like before. Well, what's that relationship between a, b, and c? Well, we knew for the ellipse, c squared equals a squared minus b squared. For a hyperbola, c squared equals a squared plus b squared. It actually is the Pythagorean theorem. And one way to see that is to say, okay, well, this distance right here, if that's a0 is a. This distance right here, okay, if that's 0b, this distance is b, and we get a right triangle here, okay, where a squared plus b squared equals c squared. That's c, and if I rotate this down, it will actually connect with the focus. So there's our right triangle with a, b, and c, and it rotates down, and I won't get into it any more than that at this time. Okay, so that's what the equation looks like if the transverse axis is horizontal. Well, just like with the ellipse, we can switch where the a squared and the b squared are. If the a squared is with the y, that's the bigger number, we actually end up switching it, and we have y squared over a squared minus x squared over b squared equals 1. This still relationship c squared equals a squared plus b squared is the same. We've just rotated the whole thing to be vertical instead. All right? So let's graph y squared over 49 minus x squared over 32 equals 1. Now notice the y squared's coming first. So this is a squared is 49. So a is 7. B squared is 32. So taking the square root, b is what? 4 root 2. Now we can find our c squared. C squared equals a squared plus b squared. Let's see, what is that? 81. Am I right? 70 plus 11, 81. So C is at plus or minus 9. All right, so let's start sketching this. And I'm going to just go to a graph paper here because it's going to be a little bit more detailed. All right, now we said that the y squared comes first. So that transverse axis has to be vertical, not horizontal. So we got to take everything we talked about here and just rotate it to be vertical instead. Our vertices are going to be at 7, 0, because A is 7, 0, 7, and 0, negative 7. So we're going to go 1, 2, 3, 4, 5, 6, 7. We're going to put a vertex there. And then we're going to do this one down here as well. All right, so we know the hyperbola is going to go through those 2 points like this. Okay. Now our covertices, B is 4 root 2. There it is. Oops. 4 root 2, it's about 5.65. So what I'm going to do is I'm going to come here, 1, 2, 3, 4, 5, about 0.65, and do a covertex there. I'll do the same thing on the other side. Okay. Then I really like to make that rectangle that we saw in that other graph, because it helps us draw those slant asymptotes. There we go. Okay. Now our foci are going to be at C equals 9, so that's going to be on the same axis as the vertices. So we have a focus at 0, 9. And we have a focus at 0, negative 9. Okay. So the hyperbolas are going to come and they're going to go through the vertex, wrap around the focus. Now our box is used to make those slant asymptotes I mentioned. Okay, we're going to draw a line that goes right through both of those corners. All right, so it's going to look something like this, but actually I want to extend it beyond. Like that. There we go. Like that. So now when I draw this, the hyperbola has to start close to the slant asymptote, come to the vertex, and finish close to that slant asymptote. And like that. Kind of like that. There we go. Let's put this into GeoGebra and see if it matches up. All right, so we said, what did we have? We had y squared over 49 minus x squared over 32 equals 1. There it is. So we see that vertical transverse axis. We see the vertices at 0, 7 and at 0, negative 7. We said that we had the focus at 0, 9. And 0, negative 9, like that. Now, I'm not going to put in the whole box, but what I do want to see is I want to see what those those slant asymptotes are. And the equation for this is really not that difficult when we think about how we got these points. So these are equations of lines. So I'm thinking y equals mx plus b. And what is the slope of this line? Well, the rise is the distance to the vertex, which was 7. The run is the distance to the co-vertex, which was what? 4 root 2. Again, we knew this rise was the distance to the vertex 7. The run was the distance to the co-vertex 4 root 2. So the slope is 7 over 4 root 2. And then we have x, and the y-intercept is 0 because our hyperbola is centered at the origin. Okay, so that's the first one. How about the other one? Okay, this one. Well, now we're going down 7 over 4 root 2. So the other slant asymptote is negative 7 over 4 root 2x. Let's graph those and let's see if those are our slant asymptotes. Y equals 7 over 4 square root of 2 x. Y equals negative 7 over 4 square root of 2 x. Okay, there we go. And we see the hyperbola approach both of those slant asymptotes. And that's what our graph looks like. All right. Okay, so we should feel pretty good about that. Now, let's go to that distance thing. Now, do you remember that on the ellipse, if I sent a segment from one focus to a point on the ellipse to the other focus, that distance, that sum, when we add those two distances together, were always the same no matter where we were on the hyperbola. Well, what I'll do right now is I'll put a point on the hyperbola. And just like with the ellipse, I'm going to run a segment from D to that point, and then from that point on the hyperbola to the other focus, just like this. All right. Now, here are those distances, 7.65 and 21.65. And what I'm going to do right now is I'm going to take the one distance I and subtract the other distance, which is h. So I'm taking the long one minus the short one, and I get 14. And notice, wherever I am on the hyperbola, that the difference between those two distances is always 14. Notice how the h and the I are changing, but when I find that difference, it's always 14. And the way that I remember that with the ellipse, the sum of the difference is always the same, and the ellipse equation has that plus in it, where in the hyperbola equation, we have a minus, and it's the difference of these two distances that's constant. That's always the same. So there's our introduction to the hyperbola. We're going to come back in a second video, look at another example.